unmuted. So I guess, oh.
Did we lose her? No, there she is.
So, yes, we are ready to start. So, can you hear me, Alex?
Yep, I can hear you. Hi.
Yeah, today's speaker is Aleksandra Hamanowicz from Space Telescope Science Institute, and she'll be talking about the CGM work she's been doing there. Please take it away.
Okay, thank you very much for inviting me to give that talk. I am very happy to be virtually visiting Caltech, and hopefully sometime I can come there in person too. I would like to introduce myself a little bit more because I'm a bit new to the American scientific community. I'm originally coming from Poland, and I did my PhD in European Southern Observatory in Germany, where I was mostly working on the ground-based telescopes. But then I moved over a year ago here to the United States, to Maryland, to work on Space Telescope Science Institute, and now my work it focuses mostly on using UV spectroscopy and Hubble Space Telescope in general. So as the ESO symbol already tells you, majority of what I'm going to tell you about is what I was working on during my PhD. And I'll give you a bit of a hint of what I'm interested in right now and the work in progress, which hopefully soon will be also published. So let me start with a general introduction of and the structure of what we are going to talk about today, because baryon cycle, which is the topic of my talk today, it's general very broad topic and generally a very broad science case, which has a multiple different questions which we try to answer on majority of different scales and in different environments. So when I'm thinking about the baryon cycle, I am thinking about it in a two different, let's say, environments or scales. And that's also how my talk will be divided in those two different scales. So from one side, we have the local baryon cycle. And by local, I mean local to a galaxy, not necessarily Milky Way. Here, we are thinking about all of the gas flows which are happening around the galaxy, in and out of the galaxy, which can transport the gas from the intergalactic medium onto the interstellar medium, and the other way around, where for different processes, we can expel the gas outside to the intergalactic medium again. And this area of where most of this gas motion is happening is called the Circum-Galactic Medium. And it's the main interest of mine when we are thinking and talking about the local baryon cycle. Then we can also think about a baryon cycle in a much larger scale when we think about it in a very global way. And here by global, I mean the universe as a whole. And here we can try to understand how the gas in universe and its different phases changed how much of the gas we are seeing in different phases throughout the history of the universe, and compare that to how the star formation history of the universe goes on. And here on this plot on the right, I'm showing you how different phases of the gas change a change in the density throughout the history of the universe, from the molecular gas, which will be the main interest of my talk in the second part of that talk, but also in how much materials actually lock down in stars and how the neutral gas also looks in comparison to that. And there are many interesting aspects about this global baryon cycle and how it can relate to how many stars are being formed and why are being formed this way and on the other. So these will be the main two topics, and generally showing my interest in tracing the baryon cycle on the very different scales at the very different epochs. So let's start from this local baryon cycle, the very when we're thinking about the Milky Way like galaxy, it can be at a very different redshifts, but what's actually happening throughout the life of a galaxy and how much this gas, with which it interacts, influences its history and evolution. I think we can start from the fact that galaxies are not systems which are evolving as a single alone islands. They are not evolving in isolation. They are very much interacting with all of the medium, all of its environment, and that's really affects how they evolve and what kind of properties they will have. So the main cycle, which I'm also trying to depict here in form of this circle of what is happening, a circle of general processes which are happening, is exactly the representation of that local cycle of baryons. So when we are thinking about the galaxy and its evolution, it's driven by how it forms stars and how many stars it's forming. So when we are forming stars, we are using gas, and this gas comes from the interstellar medium of that galaxy. But with time, to keep forming those new stars to the level which we, for example, observing nowadays, the galaxy cannot just be locked up and it would use up all of its material already. So it has to replenish the gas, which is used for star formation, and this gas has to come from somewhere, from outside. But the more gas is accumulating on the stars, it fuels the star formation, and in turn, star formation actually causes the gas to be expelled from the galaxy. The strong winds from the massive stars and majority, the very high velocity ejecta from supernovae can drive the gas away from the stellar medium into this surrounding big halo around the galaxy, which we call circum-galactic medium. Naturally, some of that exhaled material will fall back into the galaxy. Not all of it has enough speed to escape the potential gravitational potential of the galaxy. However, we know about the galactic winds, which can actually cause this, or of course, the AGN activity can also expose those gas far away from the galaxy. But one important aspect about this is that also that expelled material, in the contrary to the one which we think is being accreted from the intergalactic medium, which usually is quite metal poor, this material which is being recycled inside of the stars is being now enriched. So when we are thinking about the whole cycle of baryons, it's not exactly the same material which is coming and going. We are accreting more and more of this metal poor material. It has to come from outside of the system, while when it's being transformed in stars in the interstellar medium, it's much more, it's enriching the galaxy environment in metals. So why this, in general, this local cycle of baryons is of any interest to galaxy evolution? Well, I wrote here three keywords, which already I mentioned two of them. But those are three elements of with galaxy evolution, which are connected very much to the cycle of baryons on a local scale. Star formation obviously is the main driver of this, and feedback would be another. General feedback and star formation altogether is basically what I was describing so far. And then the question of quenching can find its solution also in the way how this local cycle of baryons is happening. So for one side, we can think that if there is in any way this inflow of the gas from outside is being blocked, that's why at some point the galaxies can become too quenched because they do not have enough material to form new stars. How much it is of the case and how much actually what's happening in the circumgalactic medium affects the evolution of galaxies is still the open question, and that's why I want to study it more. So let's talk a little bit about the techniques and about how we can study circumgalactic medium. I guess some of you are interested in that topic already, as well, just a recap. But let's see into one of the challenges, one of the questions are of the nowadays area of observing the CGM. So I'm showing you here the figure from the COS halos, which are very nicely showing how we are trying to study this gas in circumgalactic medium. So let's start from the fact that this gas is a very faint, very diffuse, and with a very big range of temperatures. And most of it is generally impossible to observe in emission. There are multiple simulations which are showing that in the future telescope we might get this very faint light of CGM. But right now, we only saw it around the very strongly ionizing sources like the very bright quasars in form of Lyman alpha nebulae. For a typical star-forming galaxy as a Milky Way right now, we are basically impossible to see this gas glowing in emission. Therefore, we have to look for ways to study it, which would be different and will not depend on the emissivity of the gas. And here comes the absorption. The strength of the absorption will only depend on how much material there is and how bright is our background source, on which light we see the imprint of the gas we are trying to observe. And here on this figure, we can see that when we are pointing our telescope towards a very distant background quasar, usually quasars are point-like sources on a very high brightness, and they are very good sources, those background sources to study, to do this kind of studies. Then if the light of the quasar will be going through some CGM gas around some of the galaxies, we will see the imprint of this gas in the form of the absorption lines on top of the emission spectrum of the quasar. And this is how we identify all of those quasar absorbers, which we are using to study circumgalactic medium. But now, there's one thing which I'm going to repeat multiple times is how we are defining the position of the sightline in respect to the galaxy, which we think that circumgalactic medium is connected. We call it the impact parameter. And for the elsewhere galaxy or Milky Way type of galaxy, we usually regard circumgalactic medium to go as far as 300 kiloparsecs. So what can we say? What can we say about this gas in CGM by using the absorption lines? Well, obviously we can tell something about kinematics and trying to trace the flows of gas, which I was describing before, whether it's inflowing or outflowing from the system. By tracing different elements, we can say something about the metallicity. And here again, we can try to compare the metallicity of the gas to the metallicity of the host galaxy and try to decide whether we are talking about the gas outflowing, so being enriched by the star formation, or it's being inflowing, which we usually regard as the one which is metal poor. But there are questions which probably already are coming to some of your minds. Is like, okay, we look at some different distant quasar and we are seeing the absorption lines into it, but how do we actually associate the galaxy? How we find the galaxy which is a circumgalactic medium belongs to? And that's one of the biggest questions actually right now. Is the fundamental, but it's quite big. And then we have to try to study this associated galaxy, to understand what are the properties and how this galaxy seem to interact with this gas that you see in absorption. So there are many different techniques which we can try to use to try to answer exactly those questions. And the way of finding the hosts of those quasar absorbers in the recent years became much more easy thanks to the 3D integral field unit spectroscopy. In this kind of spectroscopy, well, we are combining the imaging and spectroscopy. For each pixel in our field of view, we get a spectrum, we get a light spectrum. Therefore, each of our objects which we can detect immediately can be classified spectroscopically. So of course that saves us a lot of time on the telescopes by trying to identify the photometric images and then follow up the spectroscopy to get the redshifts. Here we go all in one go. And what I'm showing you here and on this plot on the right is one of the example of the quasar fields with the known quasar absorbers from MUSE integral field unit spectroscopy. MUSE is the IFU on very large telescope on VLT in Chile, which has one arc minutes field of view. and allows us to exactly this kind of study. Very nice. Additionally, if we don't have to only look for objects which have strong or clear spectra, so normally what we in the integral fusion spectroscopy immediately we pick up objects which have bright emission lines, but also we can collapse the cube along the wavelength axis, getting a continuum image, and then measuring and looking for the continuum of more continuum objects. So there's very powerful tool exactly for detecting very faint and objects, which then we can find to be associated with the absorption. And using exactly this tool, MUSE, we built a survey of 13 strong Lyman alpha absorbers at the redshift below 1.4. Here we were limited by the wavelength coverage of MUSE, where at 1.4 we will be losing the O2 emission line from the wavelength coverage of MUSE, so therefore we had to cut there. And we had those 13 observers at the 5 quasar fields, and the example of the kind of multi-wavelength data which we are combining here is here on the left, where we have from the top we have the MUSE image of the quasar field with the different colors. I'm marking the galaxies associated with different quasar absorbers. Then on the right we have Hubble Space Telescope image, which helps us to resolve those objects and also to look for the much more fainter object that maybe we could not exactly detect with MUSE. And then again, MUSE gives us spectral information, and we have the information about the absorption coming from the UVS spectrograph also at VLT. The name says MUSE and ALMA. I'll be mostly focusing on MUSE and also the UV spectroscopy. However, for some of those sources, we also have ALMA observations, and we detected in one of the sources, we detected the CO emission from one of the associated galaxies. And for that, I can refer you to one of the MUSE Halo papers if you're more interested in that, or I can answer some questions later. One other thing where MUSE becomes a very important and very helpful tool in hunting for galaxies associated with the quasar absorbers is the fact that we much more easy can take a look at the objects that are very close on the sky to the quasar itself. And before it was requiring a quite complicated decomposition of the PSF of the quasar. Even on the Hubble Space Telescope images, sometimes those galaxies will be hidden under it. But with MUSE, we don't have to do it in 2D. Instead, we can just look at the spectrum of the quasar and look for the emission lines at the redshift of the absorber and see if we can see anything. And indeed, in 2 cases, we managed to discover the galaxies which are very close to the quasar, just by extracting the quasar continuum and looking at the emission lines which were left and were corresponding to the redshift of the actual absorber. So this is what I'm showing here on the left. So what are the main results of the MUSE-ALMA Halo survey? Well, here comes the main, I would say, surprise was the fact that we were not finding singular galaxies associated with those absorbers. If you come back to the pictures I was showing you in the beginning, when we had a big galaxy and had those gas flows all around it, we could think that the Circum-Galactic Medium, the space absorber, would be very easy to just one absorption, one galaxy. Excuse me. However, what we found is that we find a wide range of objects which could possibly be associated with this gas which is in absorption. Yes, we have a single object cases, but we also have pairs, we have triplets, and we have small groups. And in one case, we have very rich group, which corresponds to the very high column density gas, which seem to be in the middle of the group with any of the major galaxies being nearby. Therefore, that brings the question, if this high gas content is being found in the middle, basically between the galaxies, and we are not talking about the impact parameters of 10 of kiloparsecs. We're sometimes talking about hundreds of kiloparsecs. Does it mean that what we are seeing here is not necessarily just this simple picture I was drawing at the beginning, where we have this circumgalactic medium basically describes so inflows and outflows and this recycling of gas? But when we are coming and talking about the environment, we start to see and have this complication of the interactions between the group members. And some of this gas which we are seeing might actually be the tidal streams or the remnants of the tidal interactions in between those objects. To try to understand this, we are trying to look into this impact parameter wavelength space at all of those objects. This is a rather complicated plot. I would not like to spend too much time on this, so if you're curious, I can come back to that later during the questions. But just to say, what we see here quickly is in the gray, I'm showing you where the absorption line is in the velocity space. So some of those absorptions are quite broad, some of them are very narrow. And then in blue and red, I'm showing you where are the galaxies. So on y-axis, we have velocity with respect to the zero velocity is the galaxy, which is the closest from the sky to the quasar. And then on the x-axis, we're seeing in kiloparsecs how far the other galaxies are from the quasar. So in the very first glance of it, what we can see is that we have a variety of cases of how the in velocity space where our galaxies are in respect to the gas. Sometimes we have, as on the very top left corner, we have all of the galaxies being on the negative velocity side of the gas. In other cases, we have a combination of those. Sometimes we are seeing some objects which are very close in velocity, but are very far in impact parameter. So in this plot, the main message is that not necessarily what we think is the closest from the sky to the quasar can be really kinematically associated with the gas which we are seeing in the sideline. How to disentangle that? That's another question, and that will require much more slightly different approach and a very good high-resolution spectroscopy of the quasar absorption to try to trace component by component and try to see if we can associate those different components with different clouds of gas. Maybe be able to disentangle if this gas is kinematically connected to any of the different galaxies or only of the one, or maybe we indeed are talking about an group medium, which has completely different origin to what we were thinking of before. So those interesting results, and this of course calls for follow-up. As I said, it was only 5 quasar fields. So right now, we are expanding the sample to observe many more quasar fields with MUSE. And also following that with Hubble Space Telescope, and the paper about this expansion of the MUSE-ALMA halos is underway, so it soon should be in several months. It should be available. We also are, as I mentioned, have those observations with ALMA, which there is a typo. The second paper is already published, so. If you are interested in the molecular gas properties of the galaxies associated with quasar absorbers, that's somewhere to go and look at that. And there's also underway, we are hoping to jump on a completely different level of this kind of surveys by what is planned to be a very new wide field multi-object spectrograph on VISTA telescope. It's a 4-meter telescope, which is going to have a very big field of view, a multi-object spectrograph, and we were going to observe tens of thousands of quasar by following the whole sky spectroscopic galaxy surveys. Therefore, we'll have quasars and quasar absorbers, and also have information on all of the galaxies. But that is a thing of upcoming years. But may turn to be a completely new frontier in our studies of circumgalactic medium and associated galaxies. But we will be not talking anymore of tens of objects, but of hundreds of thousands. So that summarizes my first part of my talk, the local baryon cycle. And I'll have several points which I think summarize what I was trying to say. Well, if you, already in what I was trying to introduce in my introduction was that the both local and global cycle of baryons play a very major role in the evolution of galaxies, and understanding of its influence is crucial for us to understand how quenching works, how evolution works of galaxies, and how much that gas actually can tell us about those major questions in extragalactic astrophysics. So this studies of quasar absorbers allow us to probe this, as I call it, local baryon cycle, the metal enrichment, the gas accretion on the interstellar medium. And for that, we have to go and use the different telescopes and different techniques to try to disentangle how we can link the gases in absorption and to actual galaxies. And I introduced to you the MUSE-ALMA Halo survey, in which we discovered that strong Lyman alpha absorbers are usually happening around the grouples of galaxies, which makes the understanding of the origin of that gas in absorption a little bit more complicated, which also can affect our understanding of the local baryon cycle. So then I'm going back to that main plot and main plot which I was showing you at the very beginning, and we are going to move from the local into the global aspect of the baryon cycle. So here we are now forgetting about quasar absorbers. We are forgetting about this gas which we mostly look into in the ultraviolet, and we are going to try to focus on one of the certain question of the astrophysics: why star formation history of the universe looks as it looks on the modal Dickinson plot. Why we have a peak of star formation around redshift 2, and why since then it seems like universe is being quenching. There are multiple answers, potential answers to that question, and probably the actual answer is the mix of all of them. But one of the aspects which we can think of is whether we can link particular gas space to star formation, and because the gas is where the stars come from. So whether changing of the availability of fuel in galaxies to form stars can actually drive how the star formation history of the universe looks. So to do that, we can start off from the gas, which is the most abundant phase, gas phase in the universe, which is the H1, so the neutral hydrogen. And we have multiple studies already of neutral hydrogen across the redshifts, which are summarized here. And the one thing which we can already see when we compare to star formation history is that the shape of the general density of the neutral gas do not resemble that much the star formation history. We definitely do not see the peak above redshift 2. It's more or less flat with this very slight decline. So if it's not a neutral gas, is any other type or the gas phase can be resembling more the star formation history of the universe? Can it be maybe responsible for that? So the natural candidate number 2 will be a molecular gas, so H2. Well, molecular gas, or the molecular gas, is basically needed to form new stars. So this is the condition in which the stars are being formed in molecular class. So is the availability of the molecular gas actually connected to what we are seeing in star formation history of the universe? That's why we will be looking at the density of the molecular gas. And here I'm showing you the state-of-the-art measurements of the molecular gas gas mass density evolution with time. And what we can see immediately are those big error bars. You could basically draw a straight line for that, and which would be very similar to this almost lack of the evolution we see in neutral gas. There are hints of the actual evolution, and we can trace what we are observing so far and say, okay, yes, there is a change, and the change resembles star formation history. But in reality, it's still too early to actually say. And why actually we have those very big error bars? Well, it's because observing the molecular gas is actually pretty tricky. Starting from the fact that when we are thinking about observing the molecular gas, we have to go to something emitter, and only right now what we can use is either ALMA or VLA, which allows us to observe emission lines from molecular gas. I showed you on the left that in this big letter it's H2, but H2 molecule directly cannot really be observed in the emission for the extragalactic sources. Its transitions is simply too weak, and also it's usually excited in conditions which are not the conditions in which stars are being formed. Therefore, the second most abundant molecule in the universe, which is being excited in a very cold and dense environment, which is CO, is our usual go-to when we are trying to measure the abundance of the molecular gas in galaxies. So we have our radio telescope. We measure some CO, some intensity of CO. And here starts the long process of trying to get what we are actually trying to get from this CO flux to what we see on the left. First, we need to find out what redshift we are in. And then, obviously, we can measure the luminosity of the line. But this can be in any CO line. CO has many transitions, which many of them are brighter than the others. And it's usually not the one which we want to transform directly towards the H2, which will be observed. So how this brightness of the lines is determined is being told by the spectral line energy distribution in short SLED, which unfortunately is not that very well understood in different kinds of sources. Here, what this SLED is basically showing how for different transitions, where here being marked by J, how the brightness scales to the lowest transition, so 1 to 0 for CO. And you can already see the big range of possibilities depending on the environment of the ISM environment. We have from Milky Way going up to from our Milky Way is relatively low, and those lines are the brightness of the lines do not vary that much. But when we go towards much more extreme environments, the quasars to ULIRCs, those sleds are going all over the place. So if we are observing, let's say, CO 322 or 423, and you would like to scale down to what is actual, based on that, what is the brightness of the CO 120, we have to use one of those. And which one of those? That might be a very good question. And if you are just observing one line and just in galaxy, that's actually a problem. So let's say we decide on the sled we are using, and we have our luminosity of our lowest transition 1 to 0, and then comes the elephant in the room, the alpha CO. We have to translate the luminosity of the molecular gas which we measure from CO to actual mass of molecular gas in H2. And we know that alpha CO depends on metallicity, and we know that it's different also in different environments. But right now, we are mostly using the Milky Way value. And there's another aspect of the molecular gas measurements, which is still rather uncertain. So coming back to understanding a little bit more about this plot, is that so apart from all of the caveats which I told you about so far, which of course incorporating those big error bars, we also have the fact of how we're doing those observations. So far, those excellent surveys like Aspects or Cold Z were focusing on the small, very well-studied cosmological fields. Let's say Gibbs fields, candles, or Hubble Ultra Deep Field, where we have a lot of information about in multi-wave information about the galaxies. So when we are observing an emission line, we can directly link it to one of the galaxies getting a redshift, and then, which makes all of this much easier. However, with this approach, we have a problem with what we are at low redshifts, where we are studying only very, very small parts of the sky. Therefore, we are prone to the effects of cosmic variance. We might not have the representative sample if we're only seeing a small patch on the sky. So, as I already mentioned, the results so far are suggesting the evolution, which is similar to star formation history. So, with the peak around redshift, between redshift 1 or 2, but it might not be strong enough to explain the star formation history. But regardless of whether we follow those two trends, we can ask the different question. Okay, I would like to know much more detail how this evolution of molecular gas in the universe goes. But if we are going on following the small, very deep surveys, can we find a slightly different way to look at this problem? And this is where I'm going to introduce you the ALMACAL, where we are trying to turn the sub-millimeter interferometer, which is usually not a very good survey machine, into actual one. What I'm showing you here on the left is the sky map of all of the calibrators which are used by ALMA. And in terms of sub-millimeter interferometer, the calibrator is very important, and a lot of time is observation time is being spent on them. Basically, every several minutes of your pointing to on the sky, you have to come back to your calibrator. So over the years of ALMA ALMA operations, we have accumulated hundreds of hours on the different spots of the sky. What are the ALMA calibrators? Are just very bright point sources, sub-millimeter point sources. Most of them are blazars. We know the redshift of majority of those objects, but because it's a point source, it's very easy to remove from the science data, leaving us with a very interesting field around it, which we can use for science. So this is why I designed the survey. We designed the survey ALMACAL-CO, in which we were trying to see if we can use this kind of data to look for CO emission lines. So we looked at all of those objects, all of those fields, calibrator fields. We chose 38 fields which had the deepest data, and try to look for the CO emission lines. So what we found was another challenge. On the one hand, we get very nice detections, several very nice detections, but all of them are single lines. So when we are using the calibrators, we do not choose the spectrum. We do not choose the frequency coverage. We just get what PIs were asking for the particular science case, and for which the calibrators data was being taken. Therefore, we have to work with what we have. And unfortunately, usually those spectral coverage of our data cubes is very narrow. So it's very low probability that for a particular one redshift, we'll see two lines. And unfortunately, we had only one. Because we are using this all sky view, most of those fields do not have ancillary deep data enough to search for the counterparts. So we are having a trouble where those typical surveys are really good at, because immediately they can get the redshifts. Therefore, our classification is very challenging. So we decided to choose a slightly different approach. Instead of using a lot of observation time and going after all of those objects, first, we wanted to see if we can build something based on simulation of the brightness of the molecular gas in galaxies to try to predict what kind of transitions we're looking at. And that's how we created the redshift probability calculator, which was based on particular on the Shark's semi-analytical model, a combination of semi-analytical models. What we are doing here, we are trying to assign each of our CO detection with the CO transition probability. So let's say here on the left, I have the brightness of all of the Shark galaxies in a particular CO transition, how it varies with redshift. So I know what is the brightness of my line. So I can assume that, let's say, I think my transition is 1 to 0. So that will be a particular redshift. And I know what flux I'm observing. And then I can see how many galaxies of the simulation, well, of course, being this distribution, how many galaxies of the simulation actually will have this kind of property. And then by comparing how many compared to all of the population, we can actually create a probability function. So for each of the different, for each of the possible transition which you could observe, we assign the probability. And here we are doing something different. We do not say that we observe the actual transition. We say we include all of those with their probabilities in our calculations, because we cannot say for sure that something which has 55% probability is the one. Until we have the confirmation with the observations, we can just take all of those information and include all of those possibilities in our calculations of molecular gas mass, and in translating that into the luminosity and then to the molecular gas mass as I showed you. This all pilot project was generally a test to see if we can use this kind of not really science data to obtain something which could be complementary to what was done before with those targeted surveys. And here I'm showing you the result. So all of the previous data which I was showing you on this plots several slides before are here in dash, and the red field squares are our measurements. So I would say we're doing pretty well, even though there are multiple assumptions coming into our measurements, even though we do not have the actual confirmation of the redshift, but our probability-based approach really goes well with with all of the other observations. And of course, this is just the start. To see and to test that further, we have to go and obtain the observations, follow up our sources, and see if we were correct in our measure in comparison with the simulations. We also have to take a look and see if we can explore. We had only 38 fields. We have 1,000 calibrators, so there's many more sources which can be still hiding there. So I think with this pilot we showed that there is a potential in this method. So it will be interesting to see how that goes. In the higher sample. So in the very end, I just would like to say a few words about what I am working on right now in Space Telescope, which also connects to all of the same as I said before about the baryon cycle, but it's slightly different matter. So from one side, when we come back to the local baryon cycle, what I was telling you about that we do not really understand where this gas comes from, and when we have this environment, which influences our groups or our galaxies, which makes understanding quasar absorption a little bit harder. How about we think, where are the satellites in all of this? I mean, in my work here in Space Telescope, I'm working on the COS-SAGA project, in which we take nearby Milky Way galaxies from the SAGA project, which SAGA is trying to map all of the satellite populations of the Milky Way, nearby Milky Way-like galaxies. So I have satellite information. I have a quasar spectra of several cyclines going through some of those hosts and their satellite systems. And I'm trying to understand how this gas which we are seeing absorption can be associated with satellites. On the other hand, what I haven't mentioned at all was that among the more global baryon cycle, when we are thinking about the evolution of different gas, we can throughout the cosmic time, we can also think about the evolution of metals. And here comes the question, how actually well we know how much metal there is in the dust, at different metallicities. We know that for Milky Way, more or less. We know that for, but when we are going lower and lower metallicity, which would be similar to going to higher and higher redshifts, we start to have a problem with understanding how much metals are being locked in the dust. So how well are we actually measuring the metallicities of the higher redshift galaxies and generally of anything of a low metallicity? So we are trying to understand the depletion of metals in local low metallicity dwarfs to see what kind of trends it will be holding. And to not take this a little bit too far, I'm just going to come to my take-home points from the molecular gas part, when we are looking for the connection between star formation history of the universe and the global cycle of baryons. I showed you that we are trying to use the complementary approach to what was done before with the dedicated deep surveys, when we are trying to use the calibration data to create a multi-field survey or multi-field, rather shallow survey to complement those very deep single pencil beam surveys. And we are proposing a slightly new, different approach to classifying the transitions, the CO observations, where we are not looking at classifying exactly which transition we are talking about, but rather looking at the probability of which CO transition that would be, and then incorporate it in our calculations, which we think can be very useful when in the future we would like to really expand our studies and searches for blind molecular gas observations. And with that, I would like to end, and thank you so much for your time and attention.
Well, great talk. Thanks, Alex, and take questions. Sure, Lee, go ahead.
Oh, thanks, Alex. That's interesting. I had a question about the MUSE data, because with the MUSE data, you also have a snapshot of the activity of all your sources in the group, and more than just a redshift of the source, you can study the multiple lines, and you could see, it gives you sort of a immediate snapshot of which of the objects might be pumping out gas or not pumping out gas. So you get a little indication of the history with the distance. And Mike gave a talk the other day that was really interesting, where he was talking about the different radii and how long it takes to get gas out at different radii. Yeah. So I think there's a lot more information in there which you could fold into a understanding of what's happening in those groups.
Yes, I did not really talk much about what kind of information we're trying to extract from this MUSE data. We measured metallicities for most of the sources, and we're trying to see if we can find any trends in the metallicities and star formations of those objects. Yeah, that's all of that is in my paper, but if you're interested, we can chat a bit more about that too.
Thanks a lot.
Christina Bade also has a question.
Hi, yeah, just a quick question. I wanted to get a sense of the range of the RMS and the spectra you can build up from like an ALMACAL database. What's like the most sensitive and to least sensitive you can get?
Mm-hmm. So this slightly depends. So in case of spectra, it's a little bit tricky because we have to combine the data at slightly different spectral coverage. In this data which I was showing, I was just looking for all of the calibrators which were used for, let's say, the same surveys. So they always were observed in the same spectral range. And then it depends on, of course, the depth would depend on how many of this kind of data we can combine. Now, from top of my head, it would be very hard for me to tell you what would be the limiting flux or RMS which we can get. Yeah, generally, depending on the redshift, we can really go quite low. But yeah, sorry, if I would need to give a number, I would have to dig back for that.
Yeah,
But
I understand.
yeah, generally, let me say it this way: different fields we have different depths, depending on how many observations there will be there. There are fields which are particularly very used very often, for which we have like hundreds of hours over. Yeah, it's very homogeneous data set. But there are some fields on which we can really go very deep.
Okay, thanks.
Lee, did you have any?
Yeah, sorry, I had a follow-up question to that one. Sorry, Gina. Alex, just more than just the, sorry, not more than, besides the depth, what about the redshift coverage in those Cal fields? Because it looked like, how far across the peak are you going to be able to get by using the ALMACAL?
Oh, it depends which transition we'll be targeting. We can go from 0 to 6.
Mm-hmm.
But not in all of the transitions. Right. For example, 1 to 0, only very low redshifts. But I do not have the figure here. But depending on the transition, we can really go far.
Okay,
so yeah, I think six is doable. Definitely, in what I was looking at the data which I had in that particular sample, I was thinking between 0.1 to 4.
Okay, so there is a chance of crossing over the peak and getting beyond 3.
Yes.
Okay, good. Okay.
It is. Yeah. Not in that what I was showing was mostly low redshift, but yes.
That's right.
And then there is a chance you always can go and look for C+ and try to get something from there, which obviously gives you higher redshift.
Thanks.
Okay, any other question? There. I guess then that's it. Thank Alex again. And yeah.
Alex.
Great talk.
Thank you so much.
Yeah,
Very nice to be there.